In this lesson, we are going to cover two things. We are going to do an introduction to thermochemistry. So we'll just kind of talk about some terms. We'll talk about heat, how energy flows. And then we are also going to do some calculations with heat of formation. So, topic for today, introduction to thermochemistry and heat of formation. So this is from Unit 9, and heat of formation calculations, enthalpy calculations are acquisition 4. So first, when you hear that word thermochemistry, thermo probably makes you think of heat. In this unit, when we are calculating heat, it is represented with the letter Q. Heat is simply the exchange of thermal energy. When we're talking about heat, heat always flows in one direction. It always flows from the warmer object to the cooler object. So if you were holding a hot cup of coffee, that heat would flow from the coffee into the coffee cup and into your hands. So one thing my parents used to say is like, close the refrigerator door, you're letting all the cold air out, when I would stand in front of it looking for something to eat. So that is a wrong statement. The cold air wasn't leaving the refrigerator. I wasn't letting the cold air out. I was letting the warmer air from the house into the refrigerator. So it always flows unidirectional, always goes from the warmer object to the cooler object. Heat stops flowing when both objects reach the same temperature. So if you had that hot cup of coffee and you left it out on the counter, heat is going to flow from the coffee to its surroundings until the coffee reached that room temperature. That heat will stop flowing when both objects reach the same temperature. Next term, enthalpy. We're going to use a capital H to represent enthalpy. Enthalpy is just our flow of energy. And when we're talking about enthalpy, it's going to be at a constant pressure. So the flow of energy at a constant pressure. So when we're talking about chemical reactions, these reactions or these changes can result in either the release or absorption of heat, depending on the work that it takes for the reaction to occur. So enthalpy is going to tell us how much energy and whether it is being absorbed or released by the reaction. Or the work done by what's called the system. So when we're talking about thermochemistry, it's going to be really important that we're always taking into account the system versus the surroundings. The system is defined as the area of the universe we are focusing on. We'll define surroundings first, and then we'll kind of put the two of them together. Versus the surroundings surroundings is everything outside the system. So here's why this matters. Let's say we're talking about the hot cup of coffee. The coffee is what we're focusing on. So coffee is the system. That means the coffee cup would be the surroundings. If we're talking about energy flow, heat is going to flow out of the coffee and into the coffee mug. So energy is flowing out of the system. Let's say we were to change our system and we were focusing on the coffee cup. Well, heat energy is flowing into the cup. So it depends, which way energy flows is always going to be hotter to cooler, but whether we're talking about if energy is flowing into the system or out of the system will really depend on what we are focusing on. All right, last two terms and then we'll get to heat of formation. Endothermic versus exothermic. So we talked about these terms when we did Le Chatelier's principle in Unit 8. Endothermic just means that energy is absorbed by the system. So if the coffee cup is the system, heat is flowing into that cup, that would be an endothermic process. We know from our unit on Le Chatelier's principle that if it is an endothermic reaction, we think of energy like a reactant. Endo meaning enters. Anything that goes into the system is like a reactant. If our reaction or our process is endothermic, the surroundings feel cold. The reason why the surroundings would feel cold is because energy is leaving the surroundings and going into the system. Since that heat leaves the surroundings, surroundings feel colder. When we're doing enthalpy calculations, if our delta H is positive, that means it is an endothermic reaction. Reactions can also be exothermic. Think of exo like exiting. Heat is exiting the system. In an exothermic reaction, energy is released by the system. We know from our unit on Le Chatelier's principle, if it is an exothermic reaction, energy is being released. We're going to think of energy as a product. If energy exits the system, that heat energy is entering the surroundings. So heat goes into the surroundings, so the surroundings feel warm. Since energy is exiting or leaving, delta H is negative. It doesn't mean we have negative energy. The negative sign just shows us that energy is exiting the system. The sign tells us which way energy flows. So those are some important terms to keep in mind. They're things we're going to be talking about throughout our unit on thermochemistry. So now we're going to get into what are called heat of formation calculations. Heat of formation is delta H sub F. Heat of formation. This is the amount of heat absorbed or released when 1 mole of a compound is formed from elements in their standard state. So heat of formation is just telling us how much heat energy does it take, or how much heat energy is released when we form one mole of a compound. Standard state is just the state of its substance in its pure form, 25 degrees Celsius, 1 atm pressure. My heat of formation of elements in their standard state is 0. Because it doesn't take any energy required to form an element that's already in its standard state. So like an example, an element in its standard state would be like carbon or aluminum, or even the diatomic elements. Think back to Brinkelhoff. Things like hydrogen, chlorine, all have heat of formations of 0 kilojoules. So how do we calculate heat of formation? The equation. This is the Greek letter sigma. We are going to take products minus reactants. So sigma, the like funky looking E, means the sum of. So we're going to take the sum of the products and subtract the sum of the reactants. N stands for the number of moles. So when we're talking about heat of formation, it tells us how much energy is absorbed or released to create 1 mole. So if we need to create 3 moles of a substance, we would have to multiply it by 3. So we're going to take the number of moles, multiply it by the heat of formation of the products, add all of those products up, and then subtract the sum of our reactants. First example. C6H12O6 plus 6O2 produces 6 moles CO2 plus 6H2O. So this is the reaction, and we want to calculate our delta H. You will also be given some data. Note that the delta H value is going to be different based on the state of matter. So like liquid water versus water in the gas state are going to have different delta H values. Alright, so we're going to calculate delta H. You can do this as one big problem, and that is perfectly fine. But what I notice is there are a lot of calculation mistakes. So what I'm going to do is calculate the products, then calculate the reactants, and then we'll put it together. Alright, so I have two products. And N is equal to the number of moles. So we're going to take the number of moles and multiply it by the delta H value. So for carbon dioxide, I have 6 moles, and then I'm going to multiply it by the delta H value of carbon dioxide. Sigma means the sum of, so I'm going to add it. I have 6 moles of water. I'm going to plug in my delta H value for water. And solve. 6 times negative 393.5 plus 6 times negative 285.8 gives me negative 4,075.8. Let's talk about units. Moles are going to cancel, and we're left with kilojoules. Now let's do the same thing for the reactants. So we're going to calculate delta H reactants. Reactants are on the left side of the arrow. So 1 mole, no coefficient, times negative 1260 plus, I have 6 moles of oxygen. Notice that there is not a value for oxygen in my data table. That is because elements in their standard state have a delta H value of 0. So you could just leave oxygen out if you wanted, but for sake of completion, I'll put it in there. Negative 1,260 kilojoules. So then last step, if I want to calculate the heat of formation, it's going to be products minus reactants. So I'm going to take my value that I got for the products minus the reactants. Sometimes I see students drop a negative. Make sure you are not dropping a negative. Products minus reactants. And we should get a final answer of negative 2,815.8 kilojoules. If you were asked whether this reaction was endothermic or exothermic, my delta H value is negative, so this represents an exothermic reaction. Heat energy is exiting the system. All right, let's try one more. Ammonia plus hydrochloric acid produces ammonium chloride. And again, we will have a data table. If you're ready to try one on your own, this would be a good time to pause the video, see if you can work this one out on your own, and then check back in when you're ready. If you need to go through another one together, stick with me. Let's start by calculating delta H products. Products are on the right side of the arrow. I only have 1 mole of my product. 1 times 314.4 is just 314.4. Now we're going to do the reactant side, left side of the arrow. 1 mole of ammonia. It has a delta H of negative 46.2 kilojoules. And again, it is the sum of, so I'm going to add it to my delta H of HCl, hydrogen chloride gas. Negative 92.3 kilojoules. So a negative 46.2 plus negative 92.3 gives me a negative 138.5. So final step, if I want to calculate heat of formation, the energy change for my entire reaction, products minus reactants. So for my products, I have a negative 314.4 minus the reactants, negative 138.5. Final answer, negative 175.9 kilojoules. This reaction is also exothermic because our delta H value is negative.